Hello and welcome to Chemspec Digital 2021. I have the pleasure to introduce the next presentation in this conference stream. However, before I do that, please note that we are recording this presentation to make it available for on-demand viewing afterwards. Attendees or the audience is invited to write their questions in the chat function, which you'll find in the top right-hand corner of your screen, so that we can have those ready for the Q&A session afterwards. So from there, I now have the great pleasure to introduce Dr. Andrea Adamo from Zyput Flow Technologies, who will be presenting single and multi-stage extraction for flow and batch chemistry applications. Dr. Adamo, over to you.
Jason, thank you for the introduction. Hello to everyone watching this presentation. So today I want to share a little bit of the work that we've been doing here at Zyput Flow Technologies to explore and pioneer complex multi-stage applications and ways to simplify their operation. So I'll start with a brief introduction on the company and then dive in. So Zyput started almost a decade ago as an MIT spin-out with the idea of commercializing tools for flow chemistry. And the company has grown substantially over the last few years. And now we have full-fledged line of gas, liquid, and liquid-liquid separators, tools for multi-stage extraction, additional tools for flow chemistry, and integrated platforms to assist batch applications. In general, we are a multidisciplinary team committed to excellence. Our longing is to improve society through innovative engineering. Zyput has been growing together with these products. We recently moved to a much larger facility to satisfy increasing demand. We also sent some time back devices in space to demonstrate that phase separation is possible with our technology also in gravity-free environment. We are headquartered in the Boston area. We have a presence in Europe, and we are present in the rest of the world through distributors. Our devices are featured in more than 100 papers and sold in every country where there's at least a little bit of flow chemistry. With this said, I would like to get into today's topic, starting actually with a question for you. So let's have a poll. The question is, what's your biggest challenge with batch? I should say both batch and flow extraction. So when you carry out your workup, what is the most bothersome thing? 1, settling time. 2, reactor utilization. 3, repeated extractions. 4 would be purity or selectivity. 5 is yield. 6 is something else. I will make a note regarding reactor utilization. This would be related if we're doing that in batch in a separation fan or tool of that kind. So I'll give you a few seconds to answer the poll, and then I'll continue. Very well. So how did we get into this? Liquid-liquid extraction is a very important step in production. Though the chemistry, the reactive parts are always the most interesting to the chemist, to the process chemist, the extraction plays a role in the general process timing and process length, I should say, and an overall yield. So these data were collected for the pharmaceutical industry, highlighting that extraction is the most common post-reaction step. Something similar is true for other industrial segments. So this is to highlight the relevance. Now, if we look at the way liquid-liquid extraction is carried out, starting from batch, typically it's carried out in the reaction vessel, and it's the settling part is carried out. The settling is carried out leveraging gravity. So I'll add here, for the sake of clarity, extraction is the chemical step. Separation after mass transfer occurs, separation is needed to separate the two liquid phases. So I'll be talking of extraction and separation, but each term maintains the meaning as we all know it. So focusing on the batch extraction, typically when a reaction is followed by an extraction, the reactor is used at half capacity because you need the space for the extraction solvent. So while this is ubiquitous and second nature to most of us, the truth of the matter is that we are losing capacity just because we have to have an extraction. So it would be nice if there was a way to actually use the entire reactor for chemistry and increase our productivity. Other challenges are related to multiple washes or multiple extractions. So if you need 2 washes, it's twice the time. If you need 3 washes, it's 3 times the time, because in the time domain, they happen sequentially. And sometimes there are no shortcuts because the process requires better purity, or it's important to increase the yield, recovering as much material as possible. Last but not least is the separation of emulsion, namely slow to settle systems. So often the process chemist spends a great deal of time to try to develop a system or have a solvent selection that makes a separation stage easy or fast. However, that first of all takes already time at the process development stage, but also sometimes emulsions do occur and the only solution is to wait for them to separate. As I said, we started as a flow chemistry technology company. So with respect to flow chemistry, the longing has always been to start from reagents and end to products in a continuously seamless way. The reality is that chemistry pieces are very well understood, developed, and there's a lot of technology available. Inline workup has been lagging behind. So Zypod started with the intent of offering a solution to get closer to the full continuous paradigm and of course its benefits. So the way we have answered to this question, the question of online extraction, is with this type of approach. So here you see tubing with 2 phases. Red is organic and actually red is water, and the clear phase is organic, is toluene over here. And so in a flow setting, the mixing will happen in the tubing with or without static mixers or other structures, other elements. And then the separation part will happen in one of our devices, except it's continuous and there is no need to wait. So how do we do that? Inside our devices, there's a porous membrane. We present the 2 phases, and one phase has preferential affinity towards the membrane, and we say that it wets it. It means that it spreads over because the 2 like each other. The non-wetting phase is the one that is repelled. Typically, we use PTFE porous membranes. As a result, the organic has affinity because of its low charge, has affinity with the PTFE and will spread over and wet the membrane. The non-wetting phase will be repelled. Now, if we establish a little bit of pressure across the membrane, we start pushing the organic through. So if we keep the correct value here, we can achieve complete and selective separation by pushing all the wetting phase and none of the non-wetting. So we accomplish this with a high precision pressure controller that is also placed inside the device. It's an integral part of the device. What this does, it keeps the correct pressure at all conditions, even if you change solvent ratio, flow rates, or boundary conditions, the device will self-adjust, providing a plug-and-play functionality. So this notion of wetting is very important because it's really what our device hinges on. So what you see here in the little clip is water dispensed on a PTFE membrane, and you see that the water beads up because it's repelled. Now we dispense it on a hydrophilic membrane, and you see that water soaks in right away because the hydrophilic membrane has affinity for the liquid, for the aqueous. And so one of the critical advantages that stems out of this membrane-based approach is actually the ability to separate emulsions. So if you have water droplets in an oil matrix, then with an hydrophobic membrane, all the organic gets drained out, and so all the water droplets are allowed to coalesce. And that's why separation efficiency is so high, because essentially the emulsion, we go around the emulsion by removing all the continuous phase. Emulsion can be also the oil in water type, so also organic into aqueous. In that case, all that is needed is really to add an hydrophilic membrane or use an hydrophilic membrane instead, so that the aqueous can be drained out and all the organic forced to coalesce. As an example, I have a little clip over here that is organic in red and aqueous in blue. They're mixed together over a stirring plate as to give this brownish looking feed. The separator readily separates it, giving you 100% red organic and 100% blue aqueous. So we have scaled up the technology across 2 orders of magnitude, going from laboratory to production. This bigger device here, we call it SEP 3000. It's our production device for a flow context. I have a slide touching upon batch applications that we believe require even greater throughput, and so we are working on a 10x increase on our current largest. So a device that will go to about 2 cubic meters per hour of flow rate. Scalability, of course, is very important for every flow chemistry application, because it's one of the key elements in order to save time in scaling up as the project moves forward from the lab to the production floor. The devices have a number of features that stem out of a combination of the selected approach and the engineering. Of course, continuous operation. They are density insensitive, so you can separate liquids with identical densities, emulsions, as I showed you. You can also do gas-liquid separation with the same device. You have the plug-and-play functionality because of the controller. Chemical resistance stems out of the selection of materials, and very small internal volume that is relevant for certain applications, high potency APIs, toxic material, explosive material, for instance, are cases where internal volume is of primary importance. So the way the technology has been deployed is essentially along 3 main directions. Flow chemistry, that's where we started from. With hybrid processes, we identify or refer to combination of batch and flow. And then there has been also a great deal of applications in the context of multi-stage extraction, because by leveraging the modularity, you can cascade devices in series as to get multi-stage operation. So for today, I'll touch upon mostly on flow chemistry and multi-stage extraction, and just have a slide at the end to tell you what these hybrid processes are about. So applications in flow chemistry, there has been a large amount, countless applications. There's more than 100 papers out featuring. I think I'll shortlisted for today some examples that highlight handling of safety, inherent safety that is gained by a flow approach when handling things that present relevant safety concerns. So this first example is from the work of Professor Oliver Kappe out of the University of Graz. Professor Kappe has been exploring the idea of using very reactive species that were not being used as much as desired from the chemistry side because of a safety concern. So the specific example is with cyanogen bromide. So what the researchers did is find a way to make it in situ and then work it up so that by having a quick separation with no headspace, inert material and very small internal volume, they control the risk associated with producing cyanogen bromide and then deploying it right after into, in general, any organic chemistry class of application. So there has been a flourishing of this type of approaches because they take advantages of features that flow offers to the process chemist, and there's demonstrations with other aggressive chemicals. Another example that I have is also started from university is an extraction of azides in flow. So in this case, there is fairly long, or at least it's 3 steps transformation that the researchers were seeking out. And one of the steps involves an azide that is very unstable and explosive. And so what the membrane separation enabled here is inline quick workup with no headspace, minimal internal volume to isolate the stream needed for the last reactive step. And also here you can go from gram scale to production. And this is actually even very safe for the academic environment where this work has been carried out. I have one more example, also of the same nature, meaning involving dangerous species. This one, however, is focused on a gas-liquid separation. So this work was carried out by Snapdragon Chemistry, that is a leading consulting chemistry company in the flow chemistry space. And they needed diazomethane, and so developed a reaction to produce diazomethane in situ. And the reaction is liquid phase, but then they add a substantial amount of nitrogen in order to dilute the diazomethane to safe limits. And by carrying out a gas-liquid separation in flow, they isolate the gas stream composed of diazomethane and nitrogen. The gas-liquid separation is very effective. The other critical advantage that it provides is that by separating completely the diazomethane in the gas stream from the liquid environment where it got generated, they eliminate all the impurities that could potentially poison a catalyst that may be used downstream. Importantly, this was a demonstration for in a commercial domain, or for commercial application, and the scalability of the application is also very important for all such type of applications. This actually got published on OPRD last December, and I apologize, I did not include the full reference. So I hope I've given you a flavor of the type of applications that you can do with inline continuous separation capabilities. Now, I'd like to take this a step further and hone in on multi-stage applications. So the way we've been tackling multi-stage application is looking not only at cascading separators, but also try to have ways to reduce the amount of solvent that might be needed to achieve a certain extractive goal. And so it is known from the literature for 100 years, probably, countercurrent schemes. So the idea in a countercurrent scheme, you have to think of it a little bit like a heat exchanger. You have the hot liquid that travels in one direction and the cold liquid that travels in the opposite one. And by doing this countercurrent scheme, you can demonstrate for the heat exchanger, but the same is true for the chemical application, that you get some. So what's the benefit here? First, let me tell you how it works. For the sake of argument, let's say that we have an organic with a chemical we want to extract. It's being pumped from the left of the screen, and our fresh aqueous solvent extraction phase comes in at the end. So the fresh liquid will contact an already depleted stream in order to get out the last bit of material, so to speak. And then this aqueous that now has captured a little bit of material gets recycled upstream to an organic that had a little bit more than before. And then it gets recycled upstream, and upstream again, all the way until it gets out. So the black arrows represent areas where you have two-phase flow. That's where you have the two phases and mass transfer occurs. So that's when physically the extraction takes place, and then the separation gives you the separated phases, each one of them. So why would you want to consider such a scheme, and why would you want to do multi-stage processing? So as everybody knows, when you have an extraction, you identify the capability of an extraction solvent or extraction phase to isolate or remove a compound by looking at the ratio of the concentrations between the original phase and the extracted phase. I should say, once you carry out the extraction, between the ratio between the organic and the aqueous. And so if your partition coefficient approaches 1, it means that you are equally distributing your solute. And so you need multiple stages in order to compound onto that and recover all your material. So if you add partition coefficient of 1, you recover 50%. If you add 5, you would recover much more. And that depends, of course, on the selection of phases. And so that's a typical case where you would look at multi-stage extraction. The other class of application is when you have actually two solutes that partition in a comparable way. So the ratio of partition coefficients is close to 1. Is the separation factor, the ratio of the two partition coefficients. And so if you cannot basically enrich much in the phase that you care for, then you have to repeat the extraction in order to amplify that small difference. So now we have established why you need multiple extraction steps. Why do you need countercurrent operation? So let's say that you are doing a one-to-one phase extraction. So one-to-one is the ratio between the phases, and your partition coefficient is 1. With one extraction, you recover 50% of material. Now, if you use exactly the same amount, not a drop more, not a drop less, but you process them in multi-stage countercurrent, by increasing the number of stages, you see that the recovery increases. So you can have, with 4 stages or 5 stages, 83%. And so the amount of mass material that you have hasn't changed. What has changed is the way you process it. And as you can see, you get a great deal of benefit, especially in the first few stages. Then the curve saturates, making any additional stage providing very small advantage. So in the general chemical engineering knowledge, this is not new. What we have seen, however, is that despite being very well known, there's a number of reasons that drive always for the need of experimental data. In general, partition coefficient may depend on concentration. So as concentration changes, you have to see what happens experimentally. There's thermodynamic models out there. However, they rely on parameters and data that may be either inaccurate or not even available for new molecular species. And so if a good guess is used in the model, then also the result that is collected from the computation is a good guess and not exact. So this points at the fact that experimental data is needed, and replicating true multi-stage countercurrent extraction is actually a tall order. So the way we've approached this is by integrating the platform all together and taking care of the engineering burden associated. So in the case of the laboratory scale, we have decided to set up for 5 devices, though you can use less or more by adding another platform. The platform uses standard fitting, so you can, so to speak, hack it, modify to your specific needs, and get real data at a very small scale through countercurrent solvent extraction. The scalability of the device implies that you can actually readily move to bigger versions if you need, so if your process requires so. So of course, we have done extensive characterization. Some of these results have been published as well. For the sake of example, let's consider the extraction of acetic acid from water with ethyl acetate. So in this plot, we show the recovery of the acetic acid as you change the number of stages, and we report both experimental data and Aspen simulation. So here what you see is that you increase the number of stages, of course the recovery increases, very much like the plots that I showed you earlier. The other important thing is that the experimental and Aspen results are within the error bar the same. The Aspen results were collected assuming 100% efficiency. So this efficiency refers to the efficiency of the mass transfer. And this is actually by design, though it may come by surprise. The reason is that the mass transfer area, where the two phases are shaken up, mixed up together, is actually designed. It's not random, it's designed. And so here, at every stage, we have complete equilibrium, complete mass transfer. We reach equilibrium. The separator also gives about 100% efficiency in separator, or close to 100% efficiency. So operation with this platform approaches or reaches theoretical efficiency that you could possibly get with that solvent system. As an additional note, if you take one black arrow with the related separator, that's a physical stage of extraction that also corresponds to an extraction stage. So in other tools like extraction columns, the extraction stage, the number of stages is actually an abstraction that comes out from data analysis. Here, the extraction stage has a physical identity as well. So going back to the presentation, there have been a number of examples, also from published literature. Was an example provided by Novartis and carried out in academia. There was this complex feed with THF, ethyl acetate, water, and a bunch of alcohols. And the extraction is carried out with the addition of water and decaying, with the objective of extracting an aqueous with all the alcohols and the organic with the more valuable THF and ethyl acetate components. So the tool was used as an optimization tool, so you can set conditions, collect data, and see what are the fractions, and use it iteratively to optimize with experimental, real data conditions for your extraction. I am close to the end of my presentation. There's one example more, is the oxidation of alcohols in flow that was done with a phase transfer catalyst after the reaction was carried out, in this case with Corning reactors, to leverage their very good residence time distribution and mixing. There's a first separation of the biphasic stream, and then a 3 stages countercurrent to recover the phase transfer catalyst. This was done at the laboratory scale and pilot plant scale with both Corning and Zyput technologies. Interestingly enough, here there was the biphasic stream was very hard to settle because of the minuscule density difference. In the lab, it settled in 19 hours. With Zyput, was readily separated on the fly. When you think of multi-stage extraction, there's a variety of aspects and technologies available. The aspects depend on the specific application, the taste and preferences of the engineers, and so on and so forth. I want to highlight something that is relevant to some industrial segments where molecules have high added value, which is the internal volume per stage. So at the laboratory scale, we offer 1 to 2 orders of magnitude of volume, internal volume less, which is important because it means that for a data point, we need 1 to 2 orders of magnitude of material less. You always have to wait for steady state in order to collect your data. So when material is expensive or scarce, definitely this proves provides very interesting benefits. We think that the ease of scale up as any flow technology is also very important, together with the ability to handle emulsions. With this said, I want to conclude with an example in hybrid to give you a flavor of the applications that we have been pursuing. So as I mentioned, one challenge that we see is the loss of productivity due to utilization of the available volume, of half of the available volume. So what we suggest, and we're actually doing, is to use the reactor at full capacity, so recover productivity and carry out the extraction in flow. So with ZFOX, we intend a Zypus platform for flow optimized liquid-liquid extraction. You pump in your extraction solvents, you control the ratio, you have engineered mass transfer so that is complete and repeatable all the times, and have continuous separation on the fly. The time it takes to do this operation really depends on the scale of separator. We already have it available at the 200 liter scale. This is 200 liters per hour. So it would be, say, pharmaceutical or general, some pilot plant type of application. And we are working on a 2000 liters per hour to go to enable the ZFOX concept at the production scale. So we've received a lot of attention and excitement for this type of application. So it would be nice actually to hear your opinion. So I'll ask you to send me an email. We are very open to criticism and feedback. So please let me know what your thoughts are on this. This takes me to the very end of my presentation. So I would like to thank first all of you for your attention. Before returning to Jason, I think we can also briefly discuss the polls before taking questions. Thank you all. Jason, please take on.
Thank you very much for that very insightful and informative presentation, Dr. Adama. Much appreciated. Well, that brings us on to the next step, where we would discuss the poll. I'm not sure, have you received the results of the poll, Dr. Adama? Has that come through to you?
Let me see. I don't see it in my window. Do you have them yourself?
We'll quickly check and get those to you. But in the meantime, what we can do is we can ask the audience to send through their questions to us. If you look in the top right-hand corner of your screen, there is a chat function where you're able to type in your question and send it to us, and then I will be able to pose that to Dr. Adama. Well, there we go. We have a question, Dr. Adama. The first question that I have is, how does this technology behave in the presence of solids?
Thank you for the question. It's a great question. So solids in general are considered the Achilles heel of flow chemistry, especially at the laboratory scale, because they clog things, they get everywhere. And what we have seen is that, of course, if you have very large amount of solids, you have slurries, flow chemistry in general, and also this technology is not really amenable. But if you have a modest amount of solids, they are totally manageable. The typical approaches would be the following. If you have solids only in one phase, you can pick your membrane, hydrophobic versus hydrophilic, as to avoid solids going through. And so let's say that you were to put sand in a water-toluene separation. The sand will have affinity with the aqueous, just be carried away without interfering with the device. You can always add a prefiltration to remove the solids and elongate the life of the membrane. That's also very commonly encountered. In some instances, we see users having two devices in parallel, so they will switch between one and the other. So there's always a device available while maintenance is done on the other. They don't seem to be stopping the game. As I said, they can be very easily managed. That's a little bit of insight. Thank you.
Okay, and I have one more question for you.
Yes.
Hopefully I'm putting it correctly. It says, what are typical extraction and separation efficiencies?
Yes. So when you carry out an extraction in flow, the mass transfer portion can be sized in a way as to have complete mass transfer efficiency. So there you get 100% mass transfer. We have actually done a great deal of work in order to provide simple tools to quickly size this mass transfer part and alleviate the effort, take it down to a couple of minutes. So you can find that on our website. Is free access for everybody. Regarding the efficiency of the separation, the separator approaches 100%. We see very small differences across scale, changing phase ratio, solvents. So generally speaking, would be in the 94, 95% to 100, depending on the specifics. Thank you.
All right, thank you. Thank you for clearing that up for us. It would seem that we have reached pretty close to the end of our allotted time, so I'm going to have to wrap up the session with that. So with that, Dr. Dama, I would like to thank you for doing the presentation. That is very much appreciated. I would like to thank our audience. Thank you very much. And thank you to the audience as well. Your presence has been appreciated as well. For interested parties in the audience, please feel free to reach out to Zygote on the platform, because they are available on the platform. And with that, I bid everybody a pleasant day further and have a great day. Thank you.